So for step number 5 and 6, orthogonalization, I'm going to create a new notebook before we do step number 5. Once again, I will import numpy and math just in case. So the matrix that we see in this picture, this basis matrix. So I'm going to call this B, np.array. Of course, I'm using the np array method, so I can use numpy attributes and methods. Its vectors are 1, 1, 0, 1, 2, 0, 1, 1, 0, 1, 2, 0, 0, 1, 2. And after orthogonalization, we will get these 3 vectors, 1, 2, and 3. So I will call this now orthogonal matrices are usually denoted with the uppercase letter Q. But I'm just going to call this B orthogonal. So we have 1, negative 1 over 2, 1 over 2, and 0. So that's just negative 0.5, 0.5, and 0. And the third one, if you multiply the scalar value by these components, we will get 0, 0, 2. 0, 0, 2. To make this orthonormal, you see here, this component is 2. It is, so this vector is not normalized. These could be normalized, but this is just by virtue of the operations. But let me show you how to normalize this. To normalize this, we must find the magnitude of each vector. And then divide each component. Oh, we can't divide in vectors and matrices. We can multiply it by 1 over the norm. So let me show you what I mean. So I will have n sub 1, n sub 2, n sub 3 for each row. So norm 1 will be equal to np dot linear algebra dot norm of the first let's just say column. So let's imagine these are columns. They're actually rows, but let's imagine these are columns. I'm going to go B 0. That's the norm of the first vector. If I want to normalize it, I'm going to go B and then multiply by 1 over the norm. Like so. It will give me the new vector 0.7, 0.7, 0. So if I return here to this picture, that's 0.7. Another way to express square root of 2, by the way, in case you didn't catch this, another way to express square root of 2 in math, so if you have square root of 2 down here, that's just 2 raised to the power 0.5. That's what I'm doing in my laptop calculator. So the square root of 2, the square root of 2, 2 over the 2 to the power 0.5 over 2, 0.7. That's what they're trying to say here. These have been normalized. If you see here, what we do is we take the first vector, divide it by its magnitude. And that's exactly what we've done here. Here. Normalized. So then if we create a new matrix, be orthonormal, then the first column in B orthonormal would be this vector. So let me run this. I cannot leave this empty. Okay. I'm just going to put 3 zeros in here just as placeholders. There's actually a method called zeros, but never mind that for now. One vector. Okay. So that's the first column of the orthonormal matrix. I'll go ahead and do the same for the others. Now, just to simplify the code, I'm going to take this bit. Okay, so just remember, this will normalize the first vector and make that the first column of the orthonormal matrix. And I'm just going to copy paste this for the other matrices. So this will be 1, 2, 1, 2. So normalize the vectors of B and orthogonalization. You can see this picture for reference. See Gram-Schmidt algorithm here. And then if I print P orthonormal, I want to let me reassign. I guess I could do this. There we go. That's the orthonormal matrix now. You can see none of its components exceed 0 or go below 0. If we were to plot these vectors, they would be orthogonal and they would not exceed a radius of 1. This is what an orthonormal matrix is. Now, let me show you how to do this using numpy without manually doing this calculation. So I will return here to show you how to orthonormalize ATA. Okay, so if you remember, ATA is that matrix. To orthogonalize it, there is a method called, let me see what it was called. It's called orth. So I'm going to go np lin algebra dot orth. This is orthonormalized, I believe. And I'm going to plug in. Let's do ATA first. Okay, there we go. So that's how you orthonormalize using Python. That's the first. So this is the matrix. This is the matrix U, right? This is U. If I come back here, that's the U matrix. Okay. And then we have the V matrix. That's step number 6. V. So if we print U, we print V. So this one 0.70. So we have the same matrix up here. And for S, we have it up here, right? We have sigma 1 and sigma 2. So for the matrix S, that would be step 4. Step 4, we put into a matrix. So step 4, we have a new matrix called S np.array, which will be, let me just reorder these. This will be sigma. So we have sigma 1 and 0. That's the first vector. And the other vector is 0, sigma 2. Okay. SUV. There's S, there is U, there is V. Okay, put these three vectors together. So I'm going to go NP. This is step. This is no, not this. We've already done step 6 at this point. But I'm just going to multiply all three vectors. I'm going to go mat multiplicate. Now mat mul takes 2 arguments at a time. So I'm going to first multiply the first 2 vectors. That's U and S. So I'm going to first multiply these together. So it will be U and S. And then this will give us a new matrix, which I will multiply with V. So NP dot matrix multiplication. This new matrix with V. And if I come back here, you can see we return to the original matrix, 10 to 511. 10 to 511. Let me type this to get the orthogonalized. So the orthogonal matrix would be the matrix. This is incorrect, by the way. This is S. This is S. The matrix U is the Gram-Schmidt algorithm applied to that. And V would be the Gram-Schmidt algorithm applied to this. So U will be let me type in text, Gram-Schmidt algorithm applied to ATA, and V is the same thing but the other way around. A times A transpose. Okay, just keep in mind that you do not apply the Gram-Schmidt algorithm to just A on its own. You have to apply this algorithm to the product of these 2 matrices. This is the distinction in SVD. Now, finally, if I bring you back to numpy, we could have done this whole thing using the SVD algorithm from numpy. So this would be SVD. Let me call it manual for lack of better words. But if you want to do this, there's a very nice method that does this whole thing in one go. So I'm going to have here SVD. The SVD method from numpy. So this will be what? NP, I think, lin algebra dot SVD. I will pass an A. And this method will return what are the return values? 3 vectors. U, SV in that order. So I'm going to go U, S, V. And if I print them all, print U, print S, print V. And you see we have the same matrices. This is V, like we have up here. This is the eigenvector. But what you would do is you would take the values and put them in a square matrix. And of course, that's matrix U. Of course, if we were to multiply these together, so if we were to perform this operation down here, oh yeah, because S is not, S I need to fix. So S, C, because we can't just multiply this vector. We need S to be a matrix. So we need S to be a matrix. Anyway, it's this matrix up here. It's exactly this one up here. This is really redundant, but what I'm saying is you'll get the same matrix back.